Now for A2, the first chapter that you will most probably learn is motion in a circle. Now motion in a circle is actually kind of like a continuation of kinematics from AS. So in kinematics, you are interested to know when in kinematics AS, it was a study about motion. You were interested to know how far an object has moved, how fast did it move, and whether was it speeding up or slowing down. And then the type of motions that you were dealing with were pretty straightforward. It was either a straight line motion or either a parabolic motion. That was what you learned in AS kinematics. It is a study about motion, but most of the motion that you dealt with was mainly either straight line motion or curve motion, specifically parabolic motion. Now, motion in a circle in A2 is actually a continuation of kinematics. Just that in this chapter, you are specifically learning about motion in a circle. Okay, so you are specifically learning about motion in a circle. All right, wait, Kai Cheng has just joined in. Yeah, hi Kai Cheng, we just started a little, okay, I'm referring to the notes here. Okay, right, so circular motion, we are only going to, it's also a study about motion, but this time, yeah, no worries, Kai Cheng, all right. So motion in a circle is still study about motion, just that it is dealing specifically with an object that moves in a circle. Okay, so when something moves in a circle, we're also interested in describing how far has it moved, how fast was it moving, and also whether was it speeding up or slowing down. Okay, so the first page here will basically tell you about certain quantities, physical quantities that you need to know. Okay, first things first, let's just say that you have an object that is at position A, and then it moves all the way to position B, following the path of a circle, like the ones that you're seeing right over here. Now, when it moves like this, following the path of a circle, it will tend to make an angle at the center of the circle. So this angle that your object has made when it moved from point A to point B, angle, you learn that it can be measured in terms of degrees or radians. There are two different units for angle. So specifically in motion of a circle, when something moves and it covers a certain angle, we are normally interested to know the angle covered in terms of radians. Okay, so we define angle in radians as just the ratio of arc length to radius of circle. You may have seen this equation before, where we tell you angle in radians for a circle is actually the arc length as divided by your radius. Okay, so this one gives you angle in radians. This one is angle where the unit is radian. Okay, now this one is actually definition of your physical quantity. In A2 questions, you will normally notice that definition questions can be broadly divided into just two types. Either is definition of a physical quantity or definition of a unit. The first statement here is actually talking about definition of a physical quantity, which is angle in radians. Now, you will also sometimes be asked to define a unit. Okay, so in our case, if we ask you to define 1 radian, what is 1 radian? 1 radian is defined as the angle subtended at the center of a circle when the arc length is equal to the radius of the circle. Okay, so this one here, the second one, is actually defining for you the unit. Okay, so if you look at this original equation here, you can only get 1 radian if, say, this one is 1 meter, the arc length is 1 meter, and the radius is 1 meter. It's 1-to-1 ratio. So you say that 1 radian is when you have arc length equal to radius of a circle. Okay, right. Then after that, if you're talking about something that moves in a complete circle, just now I talked to you about the object moving from point A to point B. What about the case where it moves a full 360-degree circle like this? Now, for the case where something moves a full complete circle, where the radius is r and the arc length is s, the arc length would actually be equal to the circumference of the circle if you make one complete circle. So the arc length is actually 2 pi r. Now it's because of this, where one full circle, the circumference is 2 pi r, that you can eventually deduce that 360 degrees is actually 2 pi radian. How do we do this? Is because you see, we know that angle in radians is arc length divided by radius, right? When you have a full complete circle of 360 degrees, your arc length is actually the circumference of your circle. Okay, it's 2 pi r. So 2 pi r divided by r, the r will cancel each other off, eventually giving you 2 pi radians. Okay, that's why we can say that 360 degrees is actually equivalent to 2 pi radians. Okay, so that is one thing to note. Now, there are also some questions, some rare questions sometimes where they will ask you to convert degrees to radians or radians to degree. So this one will be something you've learned in maths before. If you want to convert degree to radians, you multiply by pi over 180. If you want to convert from radians to degrees, you multiply by 180 divided by pi. Okay, so this one is what you will do. Now, moving on to some other physical quantities used to describe motions in a circle, you have something called angular displacement and angular velocity. Now, last time in kinematics, you learned these quantities before, specifically displacement, velocity, and acceleration. So in AS, you learn these three specific quantities and they had their own definition. Now in circular motion, you will see something similar to these quantities again, okay? But they're named differently, slightly differently, and they have different meanings to it, okay? The first one that you will encounter is something called angular displacement, given the symbol theta. And another one you will encounter is angular velocity, which is given the symbol omega. Now this W, which looks curvy and fat, is actually your Greek symbol omega. Okay, it's actually your Greek symbol omega. Okay, it is usually used to represent angular velocity. Now, when you are talking about symbol omega, some of you may think that isn't omega this symbol? This one is also the Greek symbol for omega. Sorry, the Greek letter symbol, not Greek symbol. Greek letter symbol for omega. This one last time was used to represent resistance. Now, these two symbols are actually correct to say this is correct to say that these two symbols are the Greek letter omega. It's just that one of them is uppercase, one of them is lowercase. If I tell you the letter A got two types, right? Either is a capital A or small a, right? We call this uppercase A, this one lowercase a, right? So one of these is actually an uppercase omega, one of these is actually a lowercase omega. I don't remember which one was it, okay? But strictly speaking, those two are actually still omega. Just that one of them is uppercase, one of them is lowercase, okay? Now, back to the topic. Now, angular displacement tells you how much of an angle you have turned. It is formally described as angle turned through from a reference point in a specific direction, okay? So this is the formal definition of angular displacement. It describes to you how much angle have you covered. So same like your displacement definition from AS. In AS, we say that displacement is distance from a reference point in a specific direction, right? So you notice the similarity in their definition, just that they change certain terms to adapt to circular motion. Rather than saying it's distance move or distance from a reference point, they say it's angle turned from a reference point in a specific direction. Okay, you still have the mention of reference point and specific direction here. Okay, now angular displacement is measured in SI units or radians. And then the next quantity you learn about is something called angular velocity. You can think of it as just simply telling you how much angle are you covering per second, much like the case of velocity. Velocity is telling you how fast you're moving, right? It tells you how many meters have you covered per second. Angular velocity is a similar concept. Rather than telling you how much distance have you covered per second, it tells you how much angle are you covering per second. Okay, so it's because of this we normally define it as angle turned through per unit time, measured in SI units of radians per second. It is also correct to define angular velocity as just rate of change of angular displacement, much like you did for velocity. Velocity last time you defined it as rate of change of displacement, but for angular velocity, omega, you are also correct to define it as rate of change of angular displacement. You just need to add the term angular. Now, for angular velocity, there's an equation that you can use to calculate angular velocity, which is given by this, where we tell you angular velocity is the angle turn divided by time taken. Okay. Both angular velocity and displacement are vector quantities because they have a certain associated direction. Because when we say something moves in a circle, you can clearly see that either they will move counterclockwise or clockwise. There are actually two different directions that you can consider. So they are vector quantities. Now, when something moves in a circle, we also have to consider something called linear speed, which is measured in meter per second. Now, linear speed can just be thought of as the instantaneous speed at a point, okay? So it is always tangent to the point. Here we define linear speed at any point in a circular path is always tangent to the point. It just means that if you have something that moves in a circle like this, if I'm considering certain points along its path, maybe say point A, point B, point C, or point D here, the instantaneous speed, or rather the linear speed at any of these points will always be tangent to that point itself. So for A, it was this. For B, it was this. For C, it will be this. For D, it will be this. Okay, the speed will always be tangent to that point that you're considering. So it's because of this, you can also say that linear speed is tangential velocity. Okay, now there's an equation that you will often use when you want to relate angular velocity and linear speed together. That one is V equals to R omega. Okay, the relation between linear speed and angular velocity is this equation. This one you use quite often. All right. Now, how do you get V equals to R omega? Is obtained from your equation V equals to S over theta. This one is say speed. Then this one is distance. And then this one is time, right? Now, when something moves in a circle, the distance is actually your arc length. So we know that in general, the definition of speed is distance over time. But for the case of something that moves in a circle, distance is actually your arc length. Okay, distance is actually your arc length. So just now, previously at the top of the page, it was mentioned to you that angle in radians is actually the arc length divided by your radius, right? So the arc length is your radius times your angle. So arc length is equals to r theta. If you sub this one inside here, you're gonna get v equals to r theta over t. Now you try to isolate out theta over t here. Theta over t is actually omega. Okay, so since omega is theta over t, therefore v is r omega. So that's why we can say this, no? V is equals to r omega. Okay, so I think the derivation is something that you need to know. Okay, this derivation is something that is kind of required. All right, although I never seen it being asked before, okay, but just know how it's derived lah. Okay, now for circular motion, there are also some other useful equations for you to know that are written on the boxes below here. If you look at the equation omega is equals to theta over t, this one is angular velocity, this one is angle in radians divided by time. Okay, so specifically, if you consider something that moves in one complete revolution, meaning to say I have something that starts from point A, it moves all the way back to point A itself. In one complete revolution here, if I ask you what is the angle covered for one complete revolution, it will actually be 2 pi radians. Okay, and then the time taken is actually your period. Period, you last time learned this as time taken for one complete cycle, right? Okay, time taken for one complete cycle. So when you have something that moves in one complete revolution, in terms of the angle covered is 2 pi radians. In terms of the time covered, is actually equivalent to 1 period. So if I have omega equals to theta over t, this becomes 2 pi over t. All right. And also this one, I can further rearrange it to become 1 over t, where 1 over t is actually equals to frequency. So I get 2 pi f. That's why you're getting angular velocity equals to 2 pi over t equals to 2 pi f. So bear in mind that this t here is period, okay? Time taken to complete one full complete cycle. So this is something that you will use quite often later on also. Okay, this is quite important. And then if let's just say I talk about another different equation where this time I have v is equals to s over t. This one is basically just telling you speed is distance over time. So if I have something again that moves in one complete circle like this, in terms of the distance that I cover, the distance I cover is the full circumference of your circle. So it's 2 pi r. Okay. So right now, if I use the equation v is s over t, the distance covered is 2 pi r. The time taken is again my period. I'm going to get this. And then this one, if I try to single it out, certain things out, 2 pi r over 1 over t, this one will become 2 pi rf, giving me this. Okay, so this one is also useful to know, but I'll say that this one is not as important as the first one. This first one is very important. You will use it quite often. Okay, so please remember this one. Any equation that you see inside a yellow box is something that is required to be memorized. Okay, anything that isn't generally is not required. Okay, so this covers certain physical quantity terms that you need to know when it comes to describing circular motion. So now we go to something else, something new, something called centripetal acceleration as well as centripetal force. Wait, let me just... So I think I'll go through here. Okay, now there's another quantity called centripetal acceleration. Just now we covered circular. So just now we covered angular displacement as well as angular velocity. We covered displacement and velocity. Now we go through something called centripetal acceleration, which is another kind of acceleration. Now, first consider an object that is moving along a circular path with constant speed. Okay. When we say something moves in a circular path with constant speed, it basically means something like this. Let's just say this is my starting point, and then after that, I move one full complete circle like this. Them saying that you're moving along a circular path with constant speed basically means that your instantaneous velocity or your linear speed is always the same. Just now I mentioned to you, your instantaneous speed or linear speed is always going to be tangent towards, is always going to be tangents to your point considered, right? So you see this blue color arrow here, if I tell you that I'm considering all these points where the ball is moving, the instantaneous speed or the linear speed at each of those points is indicated by this blue arrow, which is always tangent to the point itself. Okay, so when we say constant speed, it will mean something like this. If let's just say this one was at 10 meters per second, everything else at all the other points, the linear speed would remain the same. Okay, this is what we mean by something moving in a circular path with constant speed. The linear speed or the instantaneous speed remains the same throughout. Okay, now we would say that the speed is constant here because magnitude did not change. All right, if you recall from your AS last time, there's a difference between speed and velocity. Speed being scalar, you only need to consider magnitude. But velocity being a vector, you need to consider both magnitude as well as direction. So when something moves in a circular motion, it is correct to say that your speed is constant because the magnitude never changed. But when it comes to velocity, we cannot say that the velocity is constant because you notice that the direction of your velocity is continuously changing. You see, this is the direction of your velocity at the different points. So here, we cannot say the velocity is constant because direction is continuously changing. So velocity here is actually continuously changing in the first place. And because velocity is changing, we say that the object is accelerating. Again, this relates back to your AS, where we tell you that acceleration is rate of change of velocity. So as long as you have velocity change, you're going to have acceleration. So because we determine here velocity is changing, there definitely must be acceleration. Okay, the object is actually accelerating. But what is the direction of the acceleration here in the first place? So under kinematics last time, I didn't really teach you kinematics, but I'll just go through it a little for you. There is a relation between velocity and acceleration. The direction of your acceleration will actually determine how your velocity reacts or changes. What do I mean by that is, say I have a velocity acting like this. I give you 3 different cases. If say my acceleration is acting in the same direction as my velocity, you will speed up. But if my acceleration is acting opposite to my velocity, you will slow down. Now, in general, for both of these cases, direction remains unchanged. Okay. Now, what if you have an acceleration that is perpendicular to your velocity? Now, in this case here, you will actually have direction change, but no magnitude change for the velocity. Okay, so if you try to look back at the circular motion described here in the question right now, the magnitude never changed, right? It remained at 10 meters per second throughout, but the direction was changing. Okay, so it's because of that you can deduce that the acceleration must be acting perpendicular to the object's velocity or motion. That's the only way you can have your velocity changing direction, but without changing magnitude in the first place. So over here, your acceleration is actually always acting perpendicular to your velocity here. Okay, it is always acting perpendicular to your velocity. Okay, that is one thing to note here. Okay, now it's because your velocity, sorry, your acceleration is always acting perpendicular to your velocity, that your acceleration is always directed towards the center of the circle. You see, if I try to extrapolate the arrow for all of the acceleration indicated here, they all seem to come from the center, they all seem to be pointed towards the center of the circle. Okay, so that acceleration, while it's correct to say it's acting perpendicular to the object's velocity, it will also be correct to say that the acceleration is always directed towards the center of the circle. Okay, now this acceleration has a very special name to it. It's called centripetal acceleration. This centripetal acceleration continuously redirects your velocity direction, but without changing its magnitude. And this allows your object to move in a circle in the first place. So simply put, the key takeoff point here is just this. Any object that moves in a circle must have centripetal acceleration. Okay, anything that moves in a circle for sure must have centripetal acceleration. It is centripetal acceleration that allows something to move in a circle in the first place. Okay, so that is the thing that you just need to know from here. Yeah, as long as it moves in the circle, there is something called centripetal acceleration. It's the thing that causes the thing to move in a circle in the first place. Now, when it comes to calculating centripetal acceleration, there are two equations that you need to know. The first one is centripetal acceleration is your linear speed square divided by the radius of your circle. The second one is centripetal acceleration is the radius of your circle multiplied with your angular velocity square. Okay, so you need to know both of these equations. Now, how do you get the second equation here? It's because of the relation B equals to R omega that you learned before. If I tell you that AC is V squared over R, but at the same time, we know that V is R omega, you will get R omega squared divided by R squared omega squared divided by R will cancel off, the square will cancel off, giving you R omega squared. That's why we can say that AC is also R omega squared. Okay. Which one would you use? It depends on the question. If the question gives you linear speed, then you will use this. But if the question gives you angular velocity, then you will use the second one. Okay. It depends on what you're given inside your question eventually. All right. And then one last thing to note is this. Or why is AC equals to V squared over R? There is a derivation for it, but the derivation is not required inside your syllabus, so I didn't really bother to put that in. Okay, so you really just need to know that centripetal acceleration is V squared over R. There's a derivation for it. Usually your textbook will write that in, but since it's not required inside your syllabus, I actually just omitted it out. Okay. Right now, if you ask me how is it derived, I can't really derive it because I did not commit it to memory. Okay, but just know that it's V squared over R or R omega squared. If you want the derivation later on, I can probably find it out for you. Okay, right? Okay, now back to the other thing. All right. Okay, now since we have an acceleration in the first place, there must be a resultant force that causes the acceleration. This is something that you learn in dynamics AS, where you learn about Newton's second law. Remember, F net equals to ma. So that time it was mentioned that a resultant force can cause its acceleration. Rather, you must have resultant force to cause an acceleration in the first place because F net is equals to ma. So if you have acceleration, you must have net force. Okay. So since you already determined this acceleration here, there must be a resultant force that causes that acceleration. Okay, the resultant force is known as your centripetal force. Now in your notes that you have, this one probably was written as centripetal acceleration. So it was a typo error there. I've actually corrected it to become force. So in your notes that you have right now, I think this one is written as centripetal acceleration. It's supposed to be centripetal force, okay? The corrected one will be in Google Drive now, okay? So if you want to get the corrected page, you can just take it off from Google Drive later, okay? Right? So this resultant force is known as centripetal force. And same like what we learned last time, it was mentioned that F net and A are always in the same direction, okay? Resultant force causes acceleration. That is what we know. The F net causes acceleration. This is the first fact that we know. And then the second fact that we need to know is that net force and acceleration are always in the same direction. Okay. So for the cases now, we determine that there is acceleration, there must be resultant force. The resultant force is centripetal force. And additionally, that force, the centripetal force, must always be acting in the same direction as your centripetal acceleration. So this means that your centripetal force must always be acting perpendicular to your velocity or always towards the center of your circle. That one is actually shown in the second diagram that you have here. The arrow that you're seeing here is all representing the centripetal force. It is always the same direction as your centripetal acceleration. That's why it's always directed towards the center of the circle also. And that's why it's also always perpendicular to your velocity. Okay. So these two things where we say that the force and acceleration is perpendicular to your velocity or is always directed towards the center of the circle, you will make use of this knowledge in another different chapter eventually under magnetic field. So at the very least, just understand why is it like that first, okay? Because the state and explain question in the other chapter will require you to know this. Okay, now, if we have centripetal force, what is the equation that represents centripetal force? So since we say that just now, the centripetal acceleration is caused by a resultant force, if we use F net equals to ma, we can actually adapt this to circular motion where we say that centripetal force is equals to mass times centripetal acceleration. So just now we know that centripetal acceleration is either v squared over r or r omega squared. So you just sub this inside, you will eventually get Fc is mv squared over r or Fc is mr omega squared. You are basically just taking the mass multiplied with the centripetal acceleration to give you the expression for centripetal force. Okay, so this is the equations representing centripetal force. Now, one thing to note here also is that centripetal force is actually a resultant force. Okay, it doesn't exist by itself. It must be provided by an existing force, such as string tension, frictional force, gravitational force, magnetic force, and etc. What do we mean by that is something like this. If let's say I give you a block, it is being pushed by one force that is worth say 10 Newton, and then it encounters a resistive force of say 5 Newton. My net force here is actually going to be my F applied minus my R. So you see this F net, the resultant force, only came about because of these two existing forces. If I didn't have my applied force and I don't have my resistive force here, there is no F net. Okay, so F net is something that only arises when there are some other existing forces. That's what this statement is actually trying to tell you. Okay, it doesn't exist by itself. It's actually provided by some other existing force. Okay, so that is what we mean by centripetal force being a resultant force. Something must be acting as the centripetal force. Okay, there is no specific force just called centripetal force. it is actually provided by some other force. Okay, you probably get a better idea what this means after you go through some of the examples in the next few pages.